PreAP, PreCalculus. Note section 4.1. We've already determined how many roots that there are using the fundamental theorem of algebra. The number of possible positive or negative roots with Descartes' rule of signs. The number of roots that are zero based upon whether there's a coefficient or not. I'm sorry, not coefficient, whether there's a constant or not. Now we're going to determine how many roots could be imaginary. Let's think back for a moment to Algebra 2 and the quadratic function. Consider the quadratic f of x, whose graph is pictured. Notice that the graph does not show any zeros. But since it's a quadratic, there must be two roots. Now once again, this is the entire reason that imaginary numbers were invented. They were invented so that the fundamental theorem of algebra would work, even when it clearly doesn't work. Find the value of b squared minus 4ac. If you remember from Algebra 2, this is the discriminant. The discriminant is part of the quadratic formula, which we'll get into that in a moment. What does this tell you about the roots of f of x? So the discriminant hopefully I spell this right, is b squared minus 4ac. A is the leading coefficient. So in this function, f, this is a, b is the coefficient of x, and c is the constant. So we have 2 squared minus 4 times 1 times 2. This is going to be 4 minus 8, which is negative 4. What does this tell you about the roots of f of x? Now, if you remember from Algebra 2, the discriminant is going to tell you one of three things. It's going to tell you that you have either that you have no real roots, which is happening in this case, that you have two distinct real roots, or that you have one real root that's repeated, essentially. If the discriminant is less than 0, then there are no real roots, which means they have to be imaginary. So let's write that down. The discriminant is less than 0. Therefore, f of x has imaginary roots. Now I'm going to show you why, in case you don't remember, why that means that there are going to be imaginary roots. And that's by using the quadratic formula. The quadratic formula, it is a formula, which means it's an equation, is x equals, x being the roots, negative b plus or minus the discriminant, which is b squared minus 4ac, over 2a. b is 2. The discriminant was negative 4. A was 1. This simplifies the negative 2 plus or minus. The square root of 4 is 2. And the square root of a negative 1, so it's a negative 4, is I, which means imaginary. This could be simplified a bit. You could divide each of these terms by 2, since we're dividing by 2, and get negative 1 plus or minus I. Which means one of our roots is negative 1 minus I, and the other is negative 1 plus I. So long story short, if the discriminant is negative, and you take its square root, you're going to get imaginary numbers. That's why if you determine at the beginning what's the discriminant, if it's negative, you know that this has imaginary roots. Now let's get to the complex conjugate root theorem, which is pretty awesome. Since imaginary roots come from taking the square root of negatives and using the quadratic formula, what can be said about the possible number of imaginary roots of a polynomial function? Let me tell you what must be said. Imaginary roots must come in pairs. Specifically, they must occur in even pairs. It might be redundant saying even pairs, because it pairs too, of conjugates. Which leads us to the complex conjugate root theorem, but let's hold that thought for a second. First of all, why does it come in pairs? Because we are doing plus or minus, so there's going to be two of them. Conjugates is when the real number is the same and the imaginary part is the different sign. That's what conjugates are. Complex conjugate root theorem. If p of x is a polynomial with real coefficients, and a plus bi is a root of p of x, then a minus bi is also a root of px. In other words, if you find that you have an imaginary root, its conjugate is also an imaginary root. This always occurs on the ACT. Always. What they'll do is they'll give you multiple choice and they'll say, hey, 2 plus 3i is one of the roots of this function, and it's kind of a complex function. And then it says find another root. Without doing any work, you can just change the sign between those numbers, and that is going to be your answer. For the function p of x, what are the possible number of imaginary roots? Well, if we're just looking at this, and we aren't doing anything else that we've learned so far, we could say that p of x is quartic. Therefore, there are 4 or 2 or 0 imaginary roots. All 4 of them could be imaginary, a pair of them could be, or none of them could be. Now that you've gathered all the information needed in order to determine the possible combination of different types of roots, draw a table that summarizes. Tell you what, we will save this for the last part of our notes, which is putting together everything we've learned from this section. How many roots are there? How many are positive? How many are negative? How many are 0? And how many are imaginary?